Math 287, Cuesta College. I'm Joe Vasta, and I'm covering 8.6, which is RLC circuits. We'll see what those letters stand for. This is going to be one of the few lectures that will be done totally on PowerPoint. Most of this lecture is derivation and definitions, and basically you're just going to be solving differential equations in your homework, the kind you already know how to solve, and we'll be relating it to circuits. So we've got this battery here, and we have a wire, and we've connected it to both sides of the battery. And we have something called a charge. The charge we're going to write as Q of t, and it's a function of time. The battery causes a flow of charge measured in coulombs. So that's C. As the current, the charge produces the current. So we have the charge producing something called the current, which we'll call I of t. It's the rate of change of the charge, and it's measured in amperes. So we have the A there. So we have the charge, and we take its derivative. So Q prime happens to be I. And so we can write that right there. There's the Leibniz notation, and then there's the where you just have a prime there. And 1 ampere equals 1 coulomb per second, okay, because it is the derivative with respect to time. Okay, so as the current passes through the battery, there is a voltage gain. And so we have something called the impressed voltage, E of t. It's the electric potential difference between the 2 points that we have up there, and it's measured in volts. So, you know, if you've never seen RLC circuits before, you might know some of these words like volts you've seen on batteries. And really, you don't have to walk away from this lecture going, oh, I'm an expert on circuits. I am just going to make the connection between the circuits and differential equations. So if you are taking a circuits class or have to take one, you'll go, oh yeah, I know about the differential equations behind this. So in a circuit, there's going to be several components that oppose the flow of charge. As the current passes through these components, work has to be done, and loss of energy is described by the resulting voltage drop across each component. Now these components are where we're getting the RLC. Okay, so the R is going to stand for the resistor, L is going to stand for something called the inductor, and C, the capacitor. So let's go ahead to the next slide and see what we have here. There is an RLC circuit, and you can see the inductor, which is a coil, and the capacitor, and they have notations for all of those, and we have a switch that's open, there's the resistor, and there's the battery. So we better just kind of describe each of these things. The resistance, now without getting into this, I mean, we can make this, you know, if I was a physics teacher, we'd like to, you know, maybe spend weeks maybe talking about this, or maybe a whole semester doing this kind of stuff, but we need to move along so we can do other things in this class. So the resistance is going to be equal to something called R. You know, we'll use R as the shorthand, and what the resistor does is it reduces the flow of the current through that cycle there, and it's measured in ohms, okay, which is, there's an omega there, capital Omega. So that's the deal with this resistor. So now we're going to move to the coil now, which is called the inductor, and we have something called the inductance, which equals L. Now R and L are constants, and we'll talk about where those constants come from. What the coil does is it opposes the flow of current within this cycle, and it's measured in the measurement. They just used this name, henries, just like ohms. Okay, the last thing that we're going to put on this is the capacitance, and it's the storehouse. This stores charge. The capacitance we'll call C, and it's measured in farads. So we get these voltage drops within this loop here, where we have VR equals R times I. So this voltage drop due to the resistor is directly proportional to I being the current. And so this right here is a direct variation problem, and that constant of variation happens to be something called the resistance. So the voltage drop from the inductor is directly proportional to the derivative of the current. And so the constant of variation is L, which is called the inductance. And the voltage drop for the capacitor is directly proportional to the charge, and actually the constant is 1 over C. Instead of just putting C times Q, it's 1 over C times Q, and that C on the bottom is called the capacitance. So these RLC are just constants of direct variation, with a little twist on this one here. And so on our next thing that we're looking at, well, okay, so those are just positive constants from the 3 variations. And we can see that V, volts, can be ohms times amps. And that's from this one right here. So R is measured, we say that's ohms. And then I, which was the current, is measured in amperes. So that's what we have there. And then voltage could also be henries, which is this guy right here, L, times I prime, which is amps per second. And then this one right here, since the C is on the bottom, that's why the farads is on the bottom. And then we have the charge, which is coulombs over farads. And we gotta be careful, because coulombs, we don't want to confuse it with the capacitance C. So there's a lot of stuff here. Now we're going to go to Kirchhoff's second law, which says E of t, that equals the sum of the voltage drops in the loop. And E of t is the impressed voltage. So what I'm going to do for the next slide is I'm going to take these guys right here, this one, and this one, and add them up. It's the sum of the voltage drops in the loops. And so E of t is on the right-hand side. And what we can do with that I prime, hopefully you can see that that's an I prime there, is we can replace I with Q prime and replace I prime with Q double prime, and we end up getting the differential equation that we're trying to derive. And that is the differential equation that governs these RLC circuits. So let's go to our next slide. This is what we just derived, and the solution is going to be in terms of the charge. So that's what we're solving for. Q equals Q sub C plus Q sub P. Well, that's Q sub C happens to be the transient part. That's the homogeneous thing, and then we have the steady state part right there. The homework asks for not the charge, but the current. And sometimes they'll ask for the steady state current. So when you do your homework, sometimes you'll go, oh, I got the wrong answer. Chances are, 87% chance, and I'm just making up that statistic, is you probably, when you solve the differential equation, you know how you're solving this for Q, you probably boxed that. Maybe you found the initial conditions and found the C1 and C2, and then got all pissed off when you looked at the answer and saw that it was a little different. Chances are you have Q equals, and you should be, because the homework is asking for current, which is I, or Q prime, you should take the derivative of your answer. So just remember that. Okay, now, if you replace the charge with the position, and the inductance with the mass, and the resistance with the damping constant, and that kind of makes sense if you think about it, and one of our capacitance you replace with the spring constant, the voltage gets replaced with the external driving force, then what you have is you have this differential equation that we derived in last section, which was 8.5, which is the spring system. So the spring system and these circuits, in terms of the math, are the same. Should I use the word isomorphic? Maybe. But it describes the same thing, because when you have this right here, this charge, you can think of it as oscillations, and you have oscillations there. So to complete this picture, we have the solution for the spring system down there, which we've seen, YC plus YP. And those are also called the transient part and the steady state part. So your homework for this section, oh, by the way, we're done with the lecture. Your homework for this section happens to be a handout. It's included on the main page of the website, but I'll also include it within the PDF right next to this video on the website. And it's all you're doing is you're plugging, they're giving you L, R, and C, and they're giving you some initial conditions, and you're plugging things in, and you're just solving non-homogeneous differential equations. Some of them will be homogeneous. So do your homework, and I will see you next time.